SwayamPrabha. Digital India. Educated India.
We have only couple of lectures remaining. So, what I thought, I will put together some special topics in multiphase flows. And the first one is measurement of particle clusters in multiphase flows. So, in the previous module, we saw how do we measure particle phase, mainly particle size, velocity, number density, concentration, as well as the measurement of the carrier phase. But now we will specifically focus on measurement of particle clusters. So, how do we identify and characterize particle clusters? So, we have already discussed this, just a brief recap of what is meant by clustering and what is particle cluster, what is a particle cluster. So, we are already aware that clustering of inertial particles is different from the behavior of tracer particles, which are distributed randomly but uniformly in a flow. If we add tracer particles which are perfect flow tracers, so they track the flow faithfully, in that case they are distributed homogeneously. But once the inertia starts to govern the particle dynamics, then that leads to strong inhomogeneity of particle concentration, and this leads to preferential concentration or clustering. So, preferential concentration basically refers to the case where particles grow preferentially in some particular region of the flow, which refers to selective sampling of the particles in the flow. For example, as you can see here, so the particles or the inertial particles, you can see they are not uniformly distributed. They are preferentially segregated to some region of the flow, and clustering refers to the case where particles tend to accumulate and segregate. So, this is basically the same thing, but in case of clustering you can say you have intense preferential concentration effect, such that we can define the particle clusters as the group of particles which remain close to each other on time scales long compared to some time scale of the flow or some turbulent time scale of the flow. So, they remain together for a longer duration compared to the flow time scale, such that that grouping becomes important as far as the particle dynamics or particle heat and mass exchange with the carrier phase are concerned. So, the bottom line is clustering can lead to strong spatio-temporal inhomogeneity in the particle concentration field, and that can be of important concern in the application. So, this is the reason why we have to characterize the particle clusters, and we need to know how large are the clusters and how do they scale with the flow length scale. For example, turbulent EDs size, how do they scale with the size of the compared to the size of the turbulent EDs. Okay. So, what are the key quantities that we need to characterize in particle clusters? That involves cluster size, shape, local particle concentration within clusters. Local particle concentration means within a cluster what is the particle concentration or number density. As you can see here, I can define a global number density. So, if I know how many particles are there and the measurement volume, I know what is the global particle number density. But locally you see that you have regions where which is devoid of particles. So, where the number density is very small, while you have regions where it is very high. So, local measurement of number density is also required. Then velocity of the clusters, as well as characterization of void areas or the areas where we have low number density of particles. So, the characteristic scales of those void areas can also give us insight into the clustering dynamics. Now, for this purpose, what do we need? We need to have spatial distribution of particles, which can be obtained either from experiments or simulation. Here you are unable to see this. So, we can have experiments, for example, using laser sheet imaging, where a laser sheet is used to illuminate the particles and you capture the particle image, or we can have direct visualization of the particles also, like as in the shadow imaging, but in both cases we get 2D field. On the other hand, we can also have a tomographic imaging, for example, tomo-PIV, where multiple cameras are used and we can track the particles in a 3D flow field. And what you can't see here is the simulations, for example, direct numerical simulation of particles with Lagrangian tracking, or large D simulation that can also give us 3D field. So, basically, to characterize the particle clusters, you need the particle, the distribution of the particles, either 2D distribution or 3D distribution. It can be obtained either from experiment or from simulations. So, the methods that we are going to discuss is actually all the methods are applicable to simulations also. Also, when we have measurements in 3D field, but we will discuss specifically statistical characterization of particle clusters in 2D fields, but the methods can be extended to 3D fields either from experiments or from simulations. So, the first step in this case is to binarize the images. So, we have 2D images, for example, from PIV, as you can see here. This is an image where you can see many particles. So, the first step is to binarize. Binarize means we put an intensity threshold. So, here this is a grayscale image where the intensity varies from 0 to, let us say, if it is a 8-bit camera, then 2 to the power of 8, that is 255. So, if we choose an intensity threshold, then we can binarize. This means each pixel we can make it either dark or bright, in simple words. So, we can make it the intensity as 0 or 1. 0 means dark, 1 means white. So, we can binarize those. So, once you binarize, you will be able to identify the shapes of the particle, individual particle, and once you know that, then we can find the center of each particle, and that is what is done here. So, here you not only see the binarized image, but also this shows only the particle centers. So, that is what we need for this type of analysis. Okay, so, we will do the statistical analysis for using these particle centers. So, the first method is called particle counting in a box. So, in this approach, what we do is you divide the image into number of boxes. This is similar to dividing the images in case of PIV, what we call interrogation window in that case. But here we do not have second image. We do this analysis for individual images, okay, because here the first objective is to characterize the size of the particle clusters. Okay. So, you consider one image and then you divide this into number of boxes, and the dimension of all the boxes are same. Then we count the number of particles in each box and we calculate the probability of a given number of particles per box. Means you count how many particles say are there in this box, let us say 20 particles. Similarly, here 25 particles, 70 particles, like this. and then you go on doing this for all the images that you have captured in your ensemble. So, your ensemble should have sufficient number of images, let us say 1000 images, 2000 images, like that. So, you do this in each one, and then what you want to calculate is probability of finding a given number of particle in a box. What is the probability of finding, say, one particle in a box? Then you count how many boxes you have in total and divide that with the total number of boxes. So, that gives you the probability of finding one particle in a box. Similarly, you go on doing this, okay, from say one particle to say 200 particles. So, you get a probability distribution. Then if the particles are randomly distributed, in case you have random distribution of particle, the distribution of number of particles per box is actually given by a Poisson distribution. So, this is a discrete distribution. This is not a continuous distribution as in the case of Gaussian distribution. Okay. So, the Poisson distribution is characterized by the mean number of particles per cell. So, if you know the mean number of particles, you can specify the Poisson distribution, and in case of Poisson distribution, the mean is equal to the variance. Okay. So, so basically we know how the profile or how the PDF of Poisson distribution is. So, then we compare that with this experimental probability distribution that you have calculated from analyzing these images, and that is what we do here, as you can see here. So, this is the Poisson distribution. So, how do you get the mean? So, if you see, this Poisson distribution is specified only by lambda, which is the mean. So, this refers to mean number of particles per box. So, how do you calculate that? So, you can calculate what is the average number of particles you have in one image. In each image, you know how many particles are there. You just average that information in all images. Let us say you see that the average number of particles in an image is say 59. Then you know how many boxes are there in one image. So, 59 divided by, let us say here you have 16 boxes. So, that is what is lambda. So, if you know that, then this function describes the probability. So, if you put n is equal to 1, you get probability of finding one particle per box in case all the boxes, all the particles are uniformly distributed. Okay. And similarly, and you go on. So, this is the Poisson distribution, and this is the actual distribution. So, you see that they are differing. If your particles are distributed such that, if your particles are randomly distributed, for example, you do the same analysis for tracer particles. Let us say you do not put inertial particles in your flow, you put some tracer particles, and if you do the same analysis, you will get that the experimental distribution will nearly overlap with the Poisson distribution. Okay. So, you see that this is the power of invoking these kind of mathematical distributions. So, here you see that. So, what is the next step? That so you can ask, what is the size of the box that we should choose? Okay. So, there is no specific size that you should choose. In fact, you should vary the box size and see what happens. So, first you start with small boxes and then you go on increasing the box size, and that is what is done here. So, you see you have same set of images, but you change the box size. You see how the distribution now differs. So, if you use still smaller boxes, you will tend towards random distribution or Poisson distribution, because it will be more and more random. Okay. But then the question is, fine, this is fine, but how do we characterize the scale of the clusters? How this is related to cluster scale, you may ask. So, we do that by defining a parameter called D parameter or box index, which is nothing but the normalized difference of the standard deviation between the two distributions. So, you have the experimental distribution, experimental standard deviation, and this is the standard deviation of the Poisson distribution divided by the mean. Okay. Now, the magnitude of this D parameter indicates the degree of clustering corresponding to the given cell size. So, for each cell size you can calculate this parameter called D parameter, and then here you can see how this cell size correlates to this box index or D parameter here. So, here the box size, okay, is expressed in terms of Kolmogorov scale in this example. So, now you know at which box size the D parameter is maximum. So, for example, see here the D parameter is maximum and then it reduces. So, this provides you an estimate of the cluster scale, cluster length scale. Okay. And in this case, you can see here the experimental results are presented for different Stokes number, but as the Stokes number approaches about 1, or if Stokes number is of the order of 1, you see very high value of the box index or D parameter. Okay. And all of them have the same shape, that is, first it increases and then it reduces, and more or less you see that the peak occurs nearly at the same location. Okay. So, this tells you that the cluster size is of the order of Kolmogorov scale. For example, here we see that it is around 10 to 20 times the Kolmogorov scale. So, this means that the clustering process is mainly governed by the small scale EDs in this case. So, the viscous scales govern the formation of this cluster or accumulation of these clusters. So, this method, the main advantage of this method is its simplicity. It is quite a simple method. It is simple to calculate this. However, the limitations are this approach introduces extrinsically a scale in the processing. Now, you choose the box size. So, that is the problem. Okay, this can be avoided by choosing different box sizes, but how many box sizes you should consider to accurately resolve this D parameter. And another important point here is that here we get only a statistical estimate of the cluster scale. So, you see what we calculate here, this distribution is obtained by considering an ensemble of images. This is not one image, you have ensemble of images. So, that is why this D parameter actually it corresponds to one set of images. Okay. So, we get only statistical estimate of the cluster size. So, you can say we can get an average cluster length scale. The next one is radial distribution function, which is a very important quantity in general in multiphase flows. This has significance in droplet collision studies also. Let us see what it is. So, RDF or radial distribution function refers to the probability of finding another particle from a test particle at a given separation distance. So, you choose one test particle, you choose any particle. Now, at a given separation distance from the particle, what is the probability of finding another particle compared to the case where the particles are again randomly distributed. So, you will see that in all of these methods, we invoke the random distribution. We always compare with the random distribution to identify the clusters or the cluster size. So, this is mathematically expressed this way for a 2D imaging technique such as PIV. So, this is evaluated as follows. So, here for a given particle, the separation distance are measured relative to all surrounding particles. So, you have an image here and these are the particles that you have identified, basically the particle centers. So, you choose one particle and you calculate the separation distance with respect to all particles. So, you calculate all separation distances and you do this for all particles. Okay. Then you do the same thing for all images also. So, what would you have finally? You will have the separation distance. So, you will have a matrix of the separation distances, okay, that corresponds to the entire ensemble. Then you use some bin size and bin all the separation distances. Okay. So, these are known as Ri. So, you choose some Ri, okay, let us say R1, one separation distance, R2, R3, R4 and you go on. But you choose also the bin size. So, bin size means, see, R1 will be from 0 to delta R, okay, where you have this as Ri. Okay, let us make it more general. So, you have this bin defined such a way that this difference is basically delta R. So, you have a bin which is between Ri plus delta R by 2, Ri minus delta R by 2. You could understand? So, this is how you define the bin, as we have done in the case of particle size distribution, if you remember. So, you bin them basically. So, now you know in each bin how many particles are there. Now, you can imagine that if you consider a test particle, here you have another particle Ri and you have a circle of radius Ri plus delta R by 2 and this is Ri minus delta R by 2. So, you can define one annular area basically. Is it clear? So, for each separation distance you create basically a band, okay, an annular band. So, all the particles which you have captured within this bin, actually they lie in this band and this is what is this Ai, this is what corresponds to this area and the number of particles that you have identified in this band is Ni. So, how many particles you have in one band divided by area of that annular band. So, that is basically your number density at that corresponding to that space separation distance and you go on doing this for different Ris and you normalize that with the global number density. Global number density means what is your average number of images, again as we had done the previous case, average number of particles in an image divided by the area of the image. Now, here you can argue that how can we call this as number density, because number density is number per unit volume, not area, but we are doing this approximation in case of 2D imaging. You do not have 3D information. So, obviously, this will incur some uncertainty, but here the assumption is that this volume if you are working with a laser sheet imaging technique, then this volume is defined by the thickness of the laser sheet. So, that thickness is present both in numerator and in denominator. So, that gets cancelled out, which is also strictly not true. Why? Because the effective depth of the field actually varies with particle size. But we are not bringing all those complexities here. What we say is that yes, here the assumption is that the depth of field is uniform, and that is equal to the thickness of the laser sheet, that is all. And then we calculate this quantity called RDF. Now, so here you can see how this parameter RDF varies with radial separation distance. So, this is an example where we have droplets in a particle laden homogeneous and isotropic flow. So, you consider a homogeneous isotropic flow and you put some droplets. You do PIV imaging, you capture the droplet images and follow the same process. And then in each case you see so here you see the radial, how the radial evolution of RDF is. So, this value is high when the separation distance is closer, and it reduces as the separation distance increases. Now, what does this mean? So, here this actually means that, so if you consider this example, let us say RDF at some R, let us say it is equal to 2.5. RDF is equal to 2.5 at R is equal to 2. Then this means that the probability of finding a neighboring particle at 2 particle diameter is 2.5 times higher than that in a random distribution. So, this RDF value of 12 here, this means that if you consider the case of a random distribution of particles, and if you take 2 particles at this separation distance, then you will get 12 times more particle at the same separation distance. So, that is what RDF tells us. So, basically when RDF value is more than 1, you have higher chances of finding another particle, and this actually refers to clustering of particles. So, we can say that when RDF is greater than 1, we have clustering in at that scale. Okay. If RDF is equal to 1, then you do not have any correlation, and if RDF is equal to less than 1, then you have low chance of finding a test particle, or you are in the void region. So, the radial separation distance where the RDF becomes equal to 1, that refers to the cluster scale, cluster length scale, or we can call this as a correlation dimension. How far the particle concentration field is correlated? What it tells you that the particle concentration field is correlated to itself, and it will happen only when the particles come together and stay together for some time, then the concentration field is correlated. But beyond certain distance, that is beyond this average cluster scale, you do not see correlation, means that refers to the cluster length scale. And here in this example you see how the cluster length scale changes as you increase turbulence intensity, or you increase here Taylor scale Reynolds number. So, in this example you see that basically the cluster scale is higher or larger as you increase the turbulence Reynolds number. Now, there are limitations in this approach too. So, like the D parameter, in this case also it can only provide a statistical measure of cluster size. So, we may have clusters of different size, we do not know, but what we measure here is an average size. Whether cluster size distribution is broad or narrow, we do not know. But this will be more meaningful if you have a narrow distribution of cluster size, but we have no idea about that. Next thing, it is not directly linked to cluster shape or topology. We do not know how a cluster would actually look like. Here we assume isotropy. So, in this example that I have shown, that you inherently you define an annular band, means you do not care about the direction. Whichever direction the droplets or the particles are, you capture them. So, you enforce isotropy or you assume isotropy. So, that is the reason we have no idea about topology of a cluster. So, if you have a cluster which is anisotropic, let us say you have a long slender cluster, then what you get, the size that you get will not be correct. And we do not get any temporal information. We do not know how clusters evolve with time. And this is an inherent problem with 2D imaging. We image a projected RDF or we measure a projected RDF. So, you may have a cluster. So, clusters, why they should be 2-dimensional? They are 3-dimensional entities. So, you imagine you have a cluster, but you are considering one cross cut, because you are imaging a cross sectional view of the cluster only. Okay. So, in that case you have projection of the particle image, because it is 2D imaging. So, this can also underestimate or distort cluster strength due to projection effects and depth averaging. Then we have also difficulty in interpretation in polydispersed systems. So, the method we discussed, it does not care about the particle size. Whatever is the particle size, you get the same value. Okay. So, this approach is blind to particle size. However, this limitation we can avoid if we use RDF analysis of eyelids data. So, if you remember eyelids, in case of eyelids, we get planar measurement of particle size. That is, we not only know particle size, but we also know where the particles are. So, we can use the same analysis. The procedure is same, but you can do it conditional on particle size now, size class. So, you consider your size distribution. Eyelids you can use for mainly for droplet or spherical transparent particles. So, you can measure the size distribution and you divide it into size classes. Then you consider one size class of droplet or particles, you filter out others. So, now in your image you have only those particles belonging to a particular size class. You do RDF for that only. So, using that we can calculate RDF for different size classes, as you can see here, and we see that indeed we see a difference. So, certain size class have higher RDF compared to others, and this is also expected. Why? Because the Stokes number are different. Stokes number is sensitive to particle size. It varies as square of particle size. So, if particle size is different, then the behavior is different, then the clustering tendency is also different, and that is why you see this difference. And also interestingly, the correlation dimensions or the concentration correlation dimension or the size of the clusters are also different. So, in this case it may not make sense to call this as clusters, because in a cluster we do not know if you have particles or droplets belonging to one particular size class, may not be, but this shows you can interpret this as concentration correlation dimension, and that dimension is different for different particle sizes. So, we can get very deep insight by analyzing such results. Next technique is called Voronoi analysis for particle clustering. So, in case of, so what is a Voronoi analysis? So, basically a Voronoi tessellation or a diagram, it divides the space into cells around each particle such that every point inside a cell is closer to that particle than to any other particle. Let me repeat. So, here you see, imagine you have some particles here and you have drawn the Voronoi cells. How do we draw it? That is a different thing. Imagine this has been drawn. So, now let us consider this particle. Then you define this cell such a way that all points within this cell are closer to this node or this center than any other center. So, this can be visualized better way if you consider how we distribute. Let us say you are mayor of a city and you have some post office in the city and you want to assign certain locations to each post office. So, you know where the post offices are, which have been kind of placed considering the people number density map. So, you know that okay, in this city, in this area there are more people. So, let us put 3 post office. So, like that that has been done, but what you want to do is you want to assign an area to a post office and say that all belonging to that area should contact that post office. Okay. So, then you can do a Voronoi analysis and you define these boundaries. Why this is useful? Because all points within that area are closer to that post office than to any other one. Okay. So, we are here also we can do similar analysis. So, we can do this either for 2D or for 3D cases. So, in case of 2D we have non-overlapping polygons. So, as you can see here, and all these are non-overlapping. So, that is important. In case of 3D we will have polyhedra. So, basically one cell is assigned around one particle. Then what is the rationale behind selecting Voronoi analysis? Why should we do Voronoi analysis? So, basically the area around each cell is an indicator of the concentration, or you can say number density. Actually, the concentration is proportional to inverse of the area. So, if the area is large, then concentration is less. So, inherently you get a map of the concentration field. Where the concentration is high or low, you can see that. And we can do this for instantaneous images. Okay. So, we can get instantaneous particle clusters, which was not possible in the previous cases. So, and we can get local particle concentration map, as I mentioned. And there is no necessity to prescribe a length scale. We do not have to prescribe a scale like in case of D parameter a priori. Okay. This evolves, this comes out as the in this analysis itself. Then it is computationally less time consuming, and calculation of Voronoi diagram also allows characterization of voids in addition to clusters. So, the previous analysis we did not talk about voids at all, but here you can characterize voids as well. So, let us see how do we do this. So, again as I said, you first start with this is only one example. So, you start with your 2D image, then you binarize and then identify the particle centers, and then you can draw the Voronoi cells. If you use MATLAB, there is a inbuilt command that you can use to draw the Voronoi cells. So, here in this example you can see the Voronoi cells around particles. Then you plot the PDF of the normalized Voronoi area. So, you consider the area of all the cells and you make a PDF of that, and you basically normalize that with the average area. So, this is you just average all areas. Now, what is interesting is that this distribution is specified in case we have a uniform or homogeneous distribution, random distribution, which is again described by a Poisson process. So, if the particles are distributed according to the Poisson process, then the Voronoi cells should follow this PDF, and here again you compare the PDF of the PDF that you get from the experiment, the blue line, with the random Poisson process. And here what is interesting is you see that they intersect at two locations. So, these two locations basically are used to identify which are clusters and which are voids. So, you see in this case the probability is higher than that of the random process, and that is why these 2 points are chosen. While the first intersection points gives us clusters, that is you consider all areas below that, that is your cluster, and you consider all areas above this second intersection point, that gives you voids. So, like this, as you can see here, the red color shows the clusters, the cells which you have identified as clusters, and the voids using the cyan color, all the cells which you identify as voids. But the process does not stop here. Once you do this, you have to identify the individual clusters now. So, you have identified each cell if that belongs to a cluster or not, but now you need to group them. You need to group those cells which share common edge. So, if you do that, you can get individual clusters as shown here. So, here the red color shows all clusters, but here you see individual clusters which are colored in different colors. So, this is how you get the cluster map. Similarly, you can get map for voids also. So, these are some examples. How do you identify droplet clusters and voids? Then once this is done, the next step is the how do we characterize the particle clusters. So, because this is a 2D image, okay, so you can get the cluster area, you can calculate the area of a cluster, and then you can just take the square root of this area and define a circle equivalent diameter or size, okay, that is normally done. However, this does not always hold good for clusters which have large areas, okay, which are anisotropic. So, for that case we can define an equivalent ellipse. So, how do you do that? So, you know the area as well as you know the perimeter of this entity. So, using that we can calculate the major and minor axis of an equivalent ellipse. So, that is how you define the length scales, and usually we consider the major axis of the ellipse as the length scale of your cluster. But this approach has another advantage. You can also get an estimate of the anisotropy. You just take the ratio of these two. So, that will tell you how large or how anisotropic they are. Okay. So, what we have shown in our previous work that, so if you consider this approach, that if you calculate the square root of the cluster area, it can largely underestimate the length scale of the cluster. So for instance, let's say you have a cluster something like this. So this is say 1 centimeter and this is 9 centimeter. Then this will give you the answer as 3 centimeter, which is close to the shorter dimension. Okay. So you will underestimate the length scale. Then apart from this, we can also calculate the degree of particle clustering. So we want to know how strong is the clustering effect. So in that case, we can calculate the clustering index. So clustering index is again the normalized difference of the standard deviation between the two PDFs. You have experimental PDF, this is the Poisson PDF, and then you normalize. So this is called degree of clustering. So a greater value of this degree of clustering refers to large deviation from the random arrangement of particles, signifying a stronger tendency towards particle clustering. There is one more way in which we can characterize this degree of clustering is by calculating the relative number density. So now you can calculate how many particles you have in each cluster, because you identify individual clusters and you know what is the area of each cluster. So you can calculate the number density and normalize that with the global or the overall number density. So this gives you also relative number density. Okay. So if it is larger than 1, this means that local particle concentration within a cluster is higher than the average concentration, that indicates clustering. So here are some examples where droplet measurements are taken in a spray. So here you can see how the degree of clustering evolves in the radial direction. So you have a spray, measurements are taken in the radial direction, but at different axial locations. So for instance, here you see that at axial distance of 30 centimeter, as you move towards edge of the spray, the degree of clustering increases significantly. So droplets tend to cluster more, but this tendency reduces as you move down. The question is why? Why should this happen? Okay. So this is again related to the, so whenever we talk about clustering, there are three main non-dimensional parameters that we need to consider. First and foremost is Stokes number. So how the Stokes number changes, okay, as we move away from the spray center. Second thing is local loading, the mass loading or concentration. Third thing is the turbulent Reynolds number. So local turbulent Reynolds number, how it changes. Okay. And interestingly, here we compare the tendency for a water spray and an acetone spray. That is, in this case, the evaporation is negligible compared to an acetone spray, because acetone has high vapor pressure, it immediately evaporates as soon as you bring it to the atmospheric condition. So this also shows the role of evaporation on clustering, okay, which is not easy to explain. Although we see in the experiment the differences, why compared to the water spray, for acetone spray we see a stronger gradient of the degree of clustering. Okay. These things are difficult to explain, or it is not well explained. We can again consider the Stokes number and try to get an answer for this, but the evaporation rate can also play a role here. So the evaporation time scale to the time scale of the convective time scale of the droplets, that also can play a role. Okay, so this slide shows the comparison of the relative number density. So, here first thing you can see is that the relative number density here, a relative number density, this is within clusters, only within clusters we are showing this. You can calculate this for voids also. So, obviously, the value will be low. Now, within cluster we see that the relative number density is always greater than 1 and it peaks at around say 3 or so. So, this means that on average the concentration or number density within the cluster is about 3 times the overall average value, and how it changes between the water spray and the acetone spray. But here interestingly what you see here is that the plots are nearly overlapping with each other. So, this also tells us that the overall phenomena remains same if you normalize appropriately. So, this refers to self similarity in the cluster evolution process. So, the magnitudes might be different, but when you normalize them appropriately, they all overlap with each other. This means that the clustering evolution process is basically same, the basic process is same. But again, you should not generalize the results. What I mean is that, okay, this has been found in this particular injector under this operating condition. It may not be universal. Okay, so time is up. So, we will stop here, we will continue this in the next class, and few more topics are also there that I will cover.